Hello students, this is the physicist. Today we are going to discuss the confusion related to the internal and external pressure in thermodynamic work done by an ideal gas. And in this video, we will basically discuss on the conceptual aspect. We will try to refrain from the complicated math that is there in calculating the work done in a thermodynamic expansion or compression. Okay. Now, in this example, we are only going to consider ideal gases. So let's suppose we have n moles of an ideal gas that is inside that is inside a thermally insulated cylinder. So the cylinder and piston arrangement that you see in this diagram is thermally insulated. That means we are not letting the heat come inside or go from inside to outside. However, we are using a heat valve that you can see in red. This is a heat valve which we will keep closed for almost all the processes except for the ones where we have to have a isothermal process in which we have to supply some heat so that or we have to extract some heat so that when the piston expands or the gas expands or compresses, we can keep the temperature of the gas constant by supplying or removing some heat. Right. But in most of the cases, the heat valve is just there doing nothing except when we have to keep the temperature as a constant. And for that, we need to supply or take away some heat. However, let's understand the main confusion that you face is understand, imagine when the piston, as you can see, the solid black piston goes from left to right, you see you are let's the confusion is there is an internal pressure pi on the left hand side, and let's suppose when the piston is expanding and going to the right you have the external pressure p. And if understand, if the internal pressure is not equal to the external pressure, in this case how do you find when you talk about the work done by in the process of expansion or compression, we always take the infinitesimal work done, right? Because we are not sure if the pressure stays constant. It's not necessarily an isobaric process where the pressure remains constant. And if it's not an isobaric process, then dW we have to basically take as PdV, right? And then we have to integrate both sides to find the total work done. Yes. Now, when we talk about this pressure here, is it internal pressure or external pressure, right? That's the question. Yes. So let me make it very, very clear to you, right? Imagine if I define dW equals PI, internal pressure times dV, then this is or you can say elemental work done or infinitesimal, very, very small amount of work done. That is, you can say elemental work done by gas, which is why, because the internal pressure relates to the pressure of the gas on the left hand side. Imagine if I write P external dV, this becomes the elemental work done by surrounding, by surrounding, right? Why? Because the pressure relates to the surrounding pressure, right? And they are not necessarily the same. Let me give another subscript, dWg and dWs. dWg is the elemental work done by the gas. dWs is the elemental work done by the surrounding. Now, dWg might not always be equal to negative of dWs, right? Why do I use a negative sign? Is because understand, if you consider an expansion, that would be a compression of the surrounding, yes. And if you consider a compression of the gas, that would be an expansion of the surrounding. So the nature of the work done. If it's positive for the gas, it has to be negative for the surrounding. If it's negative for the gas, it will be positive for the surrounding. But this is not always true. This is not always true. Why? Because the internal pressure is not always equal to the external pressure, right? These two pressures might not always be the same. They are the same or almost the same in certain processes we will discuss, but not in general, right? So what are we going to consider? Which pressure are we going to consider? Let me make it very, very clear to you at this stage that it is always the internal pressure, never the external pressure. Why? Never the external pressure in the sense, it's we are never going to consider the work done by the surrounding. The basic reason being, right, gas is finite, surrounding is not. Surrounding is infinite. So when we do energy analysis of the surrounding, right, DWS has almost no effect of on the energy of the surrounding. It's right. Contrary to what your regular physics teacher would have or chemistry teacher would have told you, right? Don't even think of taking the external pressure as a fundamental principle. Yeah, you will be taking the external pressure in certain situations. I will discuss when, but as a main principle or a fundamental principle, do not even think of taking the do not even think of considering the work done by the surrounding, because surrounding is by definition infinite. Gas is finite, so that's why dwg has or may have a significant effect on the energy of the gas, right? And that's why we are only going to consider the internal pressure, not the external pressure, so that we can always calculate the work done by the gas or the work done on the gas. Now, with that confusion clarified, let me also tell you another startling fact that in most of the cases, in general, right, even if you're considering an ideal gas, if I give you just any thermodynamic expansion or compression, it probably will not be able to take the internal pressure. In that case, you'll have to reference to the external pressure. Why? There is a reason behind that. It's not by definition, it's because of a particular reason. Now, let us understand why that is so. I have already taken a diagram here to make it quick. Let me just copy this diagram. Now, understand, imagine we are expanding, it's a rapid process. Let's take a very rapid expansion, right? When we consider a rapid expansion, understand what happens. The internal pressure here and the external pressure here have a significant difference. The internal pressure is greater than or much greater than the external pressure. That is exactly why the piston is going to move very, very fast to the right. In that case, when the piston has already expanded, right? When the piston has already expanded, imagine if I remove, okay, ignore this red one. Now understand what happens is you look at this distribution, right? The pressure distribution on the well inside the gas, right? The pressure distribution, and look at the pressure distribution just near the piston. In a rapid expansion, what really happens is, right, what happens is here the pressure distribution, what you have is a pressure gradient, right? What you have is a pressure gradient. The moment when the piston moves, right, suddenly, what happens? there would be a rapid expansion or a very fast expansion near the piston. However, as you keep moving to the left, far from the piston, the pressure distribution wouldn't have changed that fast because gas particles are not tightly held with each other, right? There is some gap. That's why gas is compressible, right? So the pressure immediately drops just near the piston. However, it has not yet changed well inside the gas. And that's why you do not have in rapid expansions pressure inside the gas is not uniform, right? The pressure inside the gas is not uniform. So there is a non-uniform distribution. Now, we assign a particular value of pressure to a gas in a thermodynamic process, especially when we can make sure that at every stage the gas is in steady state. Steady state means it's the pressure remains uniformly distributed and the temperature also remains uniformly distributed throughout the gas. For that thing to work, this process has to be extremely slow. It cannot be rapid. So whether it's a rapid expansion or a compression, you cannot have a unique value for the internal pressure. I hope that is clear. That's why when you try to do the dW equals to PdV, the problem is here. You can't just take the pressure because you don't know what the actual pressure is because the pressure is not uniform. P will not be considered to be the pressure of the gas because there is no unique pressure of the gas in a rapid expansion process, right? So how do you calculate the work done? Now, for that, understand if it's a rapid expansion and if it's given that the external pressure, right? Understand, even if the external pressure, once again, even if it's given that the external pressure stays constant while the internal pressure changes, you can't also use the external pressure. So if it's a rapid expansion, you can't use the external pressure also because I have already made told you that for the work done by for calculating work done by the gas, never ever consider the external pressure in general, right? It has to be either the internal pressure or something else for rapid expansions, I'm saying, right? So in the only way, imagine if this piston has a mass m, right? And let's suppose if there is no dissipation in rapid expansion without dissipation. Dissipation means there is no one-way leakage of energy from the system to the surrounding or from the surrounding to the system. For example, if there is friction there is friction involved while moving the piston, in that case also, whether you are compressing or expanding the gas, both ways you will be losing energy to the surrounding because the gas has to do extra work to overcome friction, right? So let us say that there is no dissipation, no friction. In that case, you can say that, understand, imagine if the piston starts with an initial velocity u that is 0 and after the expansion the velocity of the piston is v, then it has gained some kinetic energy, right? So the change in the kinetic energy is half mv squared, right? And where does this change in kinetic energy come from? It comes from the negative of change of the internal energy. That means some of the internal energy has decreased, right? The gas has already lost some of its uh, internal energy, and that internal energy, loss of internal energy, has appeared as change in kinetic energy. The negative sign simply indicates that while the kinetic energy has increased, the internal energy has dropped. So from that you can calculate, and this exactly understand without dissipation, and we are saying if it's an adiabatic process, if it's an adiabatic process, the rapid process is adiabatic means what does adiabatic mean? No exchange of heat, no exchange of heat between the system and the surrounding. In that case, the conservation, the first law of thermodynamics says the Q is equal to change in internal energy plus W, right? Since Q is 0, that means since Q is 0, right? That is change in internal energy plus W. That means the work done is negative of change in the internal energy, right? But we already know that the negative change of the internal energy is the half mv squared. So that is half mv squared, correct? So this is exactly how you find the work done if it's a rapid adiabatic expansion without dissipation. In this case, understand, in this particular case, if mass of the piston is zero, in that case, it becomes a free expansion in which the work done also becomes zero. Free expansion, why I'm saying it's free expansion because the piston, while the gas is trying to move the piston to the right, it's not actually giving any of its energy to the piston, right? Because piston can have only one type of energy, that's kinetic energy. Since there is no kinetic energy given to the piston because it doesn't have a mass, so there is no change in internal energy, so there is no change, no work done by the gas. Free expansion, having the concept like the mass of the piston being zero. If the mass of the piston being zero means simply one thing, it's the similar, this situation is similar to expansion against vacuum. This is the same as expansion against vacuum, right? For example, imagine if I have a gas, right? Let's suppose I have a gas here inside this chamber, and let's suppose I initially have a partition. Here you have some pressure, you have zero pressure, right? Here you have gas inside on the left hand side, right? And let's suppose suddenly I just at an instant suddenly what have happened is I simply remove this partition. So what happens? The gas particles spread out, right? So when the gas particles spread out, now the pressure would definitely change, right? You would have a new pressure P dash. Of course, the pressure would drop. Why? Because the volume has increased. So the pressure P dash will be greater than P, right? However, the temperature, understand, temperature T dash will stay the same. Why? Because when the gas expands against vacuum, it is as if it has moved, basically, it has moved a piston of zero mass to get a larger volume. And in moving a piston of zero mass, it has not done any work because the piston has not gained any kinetic energy. Why? Because its mass is zero. So that's why the internal energy will stay intact. And since the internal energy U is a function of temperature, so the temperature would also stay the same. So this is what you call free expansion, and expansion against vacuum is also called Joule expansion. It's not the same as Joule-Thomson expansion. A Joule-Thomson expansion involves real gases. Joule expansion involves ideal gases. I hope you've understood this. So I'm only giving you examples where if you can't use the internal pressure, then how do you find the work done, right? Now you might be wondering, what if there is no vacuum, right? There is no vacuum on the other side, but there is a piston of zero mass, right? In that case, once again, if there is no vacuum on the other hand side, and imagine the rapid expansion happens with some pressure inside, and there is a there is a massless piston which is allowed to expand without any kind of dissipation, without any kind of restriction. It only expands due to the difference of pressure on both sides. The internal pressure is definitely greater than the external pressure. And if there is, I said, if there is vacuum, then if the piston is massless, right? Understand? Massless piston against vacuum, right? I'm still talking about rapid processes, right? So massless piston against vacuum. When you have a massless piston against vacuum, it's same as free expansion, right? And if you have a piston with mass, piston of non-zero mass, let's say non-zero mass, against vacuum. You can make a note of this actually. If there is a piston of non-zero mass, expanding a gas against a vacuum, in that case, it's not a free expansion because the mass, the non-zero mass of the piston works as a load. So the gas actually works against a load. In that case, the work done, again, no dissipation. We are not including dissipation here. No heat is getting wasted. So the work done by the gas is simply half mv squared, where mass of the piston is m, and the piston starts from rest and attains a velocity v or a speed v. That's it. So work done is half mv squared. That's simply it. Okay. Now, if it's expanding, it's half mv squared. If it's compressing, it's negative half mv squared. Right? If it's compressing, it's negative half mv squared. Right? If it's expansion. Right? Right? And you understand why it is so. When it is expanding, the gas is doing work at the cost of its internal energy. When it's being compressed, it's gaining some internal energy because there was some work done on the gas. See, in this case, I'm not considering the external pressure, right? I'm only considering whether the piston has a mass or does not have a mass. Now that is when you have a vacuum on the other side, right? Now, what if there is no vacuum on the other side, right? If there is no vacuum on the other side, then what you do? Now, that is a simple thing. Now, understand if expanding against some external pressure that is not equal to zero, if expanding against an external pressure that is not equal to zero, so what do you do? Again, if mass of the piston is zero, if mass of the piston is zero, now let us look at this. Imagine, okay, let me not use this one. Imagine if the piston is here, let's suppose there is some P external, right? And the mass of the piston is equal to zero. Now what happens? Now, of course, I said you can't directly use the external pressure because when you're considering the work done by the gas, you have to consider the internal pressure P. I can write it as PI, but I'm just writing as P to mean internal pressure. If it's a rapid process, right? Let's suppose it's an adiabatic expansion, right? Imagine if this expansion is non-dissipative adiabatic. Of course, it cannot be, if it's adiabatic, it cannot be dissipative, right? So if it's an adiabatic process and rapid, if it's an adiabatic and rapid process, then how do you calculate the work done? Simple, same thing. You have to consider, okay, if the mass is equal to zero of the piston, and the understand what happens to the external pressure here. Let's suppose the external pressure is constant. Let's suppose the external pressure is constant. So as you can see, the internal pressure initially must be greater than the external pressure. That's exactly why the piston moves to the right. Clear? If that happens, then as the piston expands, goes to the right, the internal pressure gradually drops, right? Because since the gas is is gaining volume, it is losing its what? Pressure. Yes, it's losing its pressure, and it's if it's an adiabatic process, it's also losing its temperature. Now, in this case, you can't also use the internal pressure. If it's a rapid process, the pressure is not uniform inside the gas, right? Although you should be using the internal pressure, but you can't use the internal pressure here because you don't have a uniform pressure distribution. So how do you calculate the work done? Think about it. Right, this is confusing, isn't it? Now, I'll make it clear, right? When it's rapid, understand, you can't use the adiabatic equation that is PV to the power gamma is constant. You can't use it for rapid processes because the PV to the power gamma equals to constant being the equation for an adiabatic process, right? That is only when the adiabatic process is reversible, right? That is, it is quasi-static. We'll discuss that shortly. But for now, if you can't use this to find the work done, then and if the mass of the piston is zero, then there is only one thing. You have to take the initial temperature, you have to consider the final temperature, right? Then you have to find the difference of temperature. The difference of temperature is the final temperature minus the initial temperature. And from this difference of temperature, you find the change in the internal energy, and that a negative of the change in internal energy will be the work done by the gas. Clear? I hope you understood this. And in this case, since mass of the piston is zero, the kinetic energy of the piston gained or lost becomes insignificant. Right? So the only way you can find the work done is by accounting for, of course, yes, you would say, sir, how the temperature is not uniform. See, understand, initially you record the temperature, and once the expansion is complete, you leave the gas for some time till it attains a uniform distribution. In that case, what happens to its final stable temperature? See, understand, both the final temperature and initial temperature must be stable temperatures. Right. Such questions I don't think will be there in high school level, but I'm just considering this is an engineering problem. Okay. So this is exactly now understand. Don't get confused and don't get misled into using the external pressure since it is given to be a constant. No, you can't use it. Right. Now in problems, now let's come to this easy parts. Right. Understand. Imagine whenever now we are considering quasi-static processes. Now let's talk about first reversible process. Reversible process. A reversible process can retrace its path, right? Any reversible process has to be able to retrace its path, right? So what do I mean by that? Imagine if I draw a PV diagram, a P versus V diagram of a gas, and let's suppose I start from state 1 and go to state 2, and in doing so, I take a path like this. So in this case, imagine if I follow the path from 1 to 2 like this, then for the reversible process, I must be able to retrace the exact steps. Exact steps. That means at any given instant from left to right, whatever is the state, when I reach that same displacement in the opposite direction, the same state must be attained. If it's a rapid process, it won't be possible. Right? So reversible processes have to be extremely slow, extremely, or I can say infinitesimally slow. So that in each substep, in each elemental substep that I have taken while going from 1 to 2, right, I ensure that the distribution stays uniform inside the gas. Now, if it's a reversible process, so that means what? When the process is extremely or infinitely slow, then we call it a quasi-static process. Quasi means almost, static means it's almost a static process, right? So this quasi-static process becomes reversible. Understand, not every quasi-static process is reversible, right? But every reversible process has to be quasi-static. Why? Because when the process is quasi-static plus non-dissipative, right? So quasi-static plus non-dissipative. Non-dissipative means you are not losing energy due to dissipative forces, or you are not gaining energy due to dissipative process. That when you add the two conditions, quasi-static and non-dissipative, this becomes reversible, right? So whenever you hear or you read the word reversible given in the question, you know that the process is quasi-static. Now if it's a quasi-static process, of course, now then it becomes very, very easy for you, right? So how? Because understand, if it's a quasi-static process, then the internal pressure and the internal pressure is almost the same as the external pressure. Let's call that P. And this is the pressure you take when you calculate dW equals to PdV, right? This is this pressure here. Understand? Why? Because if it's quasi-static process, the internal pressure is the same as external pressure. So whatever is given, if internal is given, you take that. If external is given, you take that. Because it doesn't matter if it's a quasi-static process, right? So now, whether it's a reversible, understand here, if it's a if you understand, if it's a quasi-static but non-reversible process, then also you can use this formula dW equals to PdV, because you can directly calculate the work done from work done by using the the integration of pressure into dV, right? So the net work done, if the process is itself just quasi-static, then the work done will be integration of PdV, right, from initial volume to the final volume. That's it. If the pressure is given either in terms of internal pressure or external pressure, it doesn't matter. They will be the same, almost the same if it's a quasi-static process. Clear? Now, if it's an isothermal process, if it's an isothermal process, understand, when it becomes an isothermal process, isothermal process, understand, in isothermal process you have to either give some heat or you have to extract some heat. If it's expansion, you supply heat, so that when usually what happens when the gas expands, ideal gas expands, the temperature tends to drop. To compensate for that drop of temperature, you have to supply some heat. Similarly, when you are compressing a gas, the temperature tends to increase. So to make sure that the temperature stays constant, you have to gradually, very, very slowly extract, so keep extracting heat, right? So it will not be adiabatic, right? So isothermal is, again, isothermal means you have to make sure that the temperature stays the same throughout the gas, so it has to be a quasi-static process. In isothermal, understand, temperature is constant. That means the change in internal energy is zero, because that internal energy is a function of temperature. If the temperature doesn't change, the internal energy does not change. In that case, whatever heat you have supplied, that is the work done by the gas, right? And understand, in this case, the work done can also be given, right, if it's a very, very slow process. Now in this case, once again, you can calculate the work done as PdV from initial volume to the final volume. Very, very easy. Now the question might have given the internal pressure or the external pressure, but you should know that quasi-static is all isothermal is also quasi-static. Since it's also quasi-static, then whatever pressure is given, internal or external, you can take either of them, right, to calculate the work done. And you should know that this work done has to be the same as the heat supplied. In isothermal, again, I'm saying in isothermal, there is, again, when you define a process to be isothermal, you have this by default is quasi-static, and it basically is reversible. Every isothermal process is reversible, right? So there is no dissipative forces involved. I hope this becomes clear. Right? So now it's not that simple to calculate the work done by a gas, as you might have seen, right? The one thing to summarize, first of all, it's the internal pressure that should be used if pressure has to be used. By default, it has to be the internal pressure, not the external pressure. When can you use the external pressure instead of internal pressure? If the process is quasi-static. That is, the boundary of the gas moves extremely, expands or compresses extremely slowly. And in that case, the internal and external pressure would also be almost the same. So you can use either, but not in general. Second, we discussed free expansion. When a piston is expanding against vacuum, if it's a rapid process, you can't use the internal pressure and you are not going to use external pressure anyway. So in that case, it depends. If it's expanding against vacuum, then what's the mass of the piston? If the piston has mass, then you find the kinetic energy gained by the piston. That has to be the work done. And if the mass of the piston is zero, then the gas is simply expanding without any piston, you can say. So the gas is expanding freely against vacuum, but rapidly. In that case, the work done is zero. Why? Because there is no kinetic energy that is given from the gas to the piston if it's a rapid process. So if it's a rapid process that is not against vacuum but some external pressure. In that case, I already told you that you have to calculate the change in. First, you have to consider the change in the temperatures from the initial to the final state, find the change in the internal energy, and if there is no dissipation, then the change in the internal energy will be the work done, or negative of the change in the internal energy will be the work done by the gas. Now, what happens? Imagine there is another popular question, right? There is another popular question. I'll just mention that. Okay, let me give you this example. Some students have this problem. Imagine I have a piston, right? I have a piston here. Let's suppose the mass of the piston is m. Now, understand, there is vacuum, there is internal pressure P, but P is not zero. The internal pressure is not zero. It's not even close to zero. It's the P is much greater than zero, let's say. And it's also given that the process is quasi-static. There is vacuum outside, right? The process is quasi-static. The piston has some mass, whether it's zero or not, we'll consider. But we know that the internal pressure is not zero. When the piston is expanding, and if the process is quasi-static, then the only way that happens if there is either the mass of the piston is extremely large, right? So that the gas is not not able to instantly push the piston, or there is some applied force which is not zero, right? Understand, in both of the cases, whether the mass of the piston being very large, or if there is an external non-zero force which is basically countering the internal pressures push to the right, in that case, to understand, even if there is a vacuum involved, it's not free expansion. It is not free expansion. Understand that. Just because there is vacuum, don't consider that it's free expansion. If there is vacuum and the piston is moving slowly despite having a high pressure, high internal pressure, that means there is some restriction on the piston, right? Whether it has immensely large mass, or there is some external force. Some understand, in this kind of situation happens when you have a piston, right? You have cylinder vertically placed and you have a piston of some mass. So in this case, there is an mg force which has to be counteracted by the PF force, or the pressure into area. Area is the cross section area of the what do you call, the piston, right? So understand, if in vertical cases here, understand, imagine if there is vacuum outside, right? Imagine if this cylinder is expanding in space, right? In that case, there is gravity. So there is an external force mg. So you can't consider this as a free expansion. Why? Because the gas is actually expanding against a load. Whether that load comes solely due to the mass of the piston, or if that load comes due to the opposing external force. In both of the cases, the gas expands against a load, so it is not a free expansion. So how do you calculate the work done? So if the pressure function is given at from the initial state to the final state, and if there is no dissipation, or even if there is dissipation, you can simply calculate W is equal to integration of P dV from V initial to V final, right? You can consider that, right? And in that case, also imagine if the mass of the piston is zero, understand, if the mass of the piston is zero, and if the force is given, the force is given actually, right? If the force is given there, whether it's constant or not, the force is given, Then, if the internal pressure is not given, see, understand, it's quasi-static, right? So in this case, you can consider the P external to be F upon A, and then use W to be P external dV. Integrate from V initial to V final. You said, how come we are using P external? Well, you can use P external because it's a quasi-static process. That means the external pressure must be almost the same as the internal pressure. I hope now this is clear to you. So if you still have any doubts, you know where to go. Don't put your questions or doubts in the comments. You can use the comment section only to suggest a new topic so that I can make another video. But if you want a proper explanation of your doubts, visit thephysicist.in/ask. I'll put the link in the description, and it's also scrolling as you can see at the bottom. You can copy the link and visit there, register and ask your doubt. I'll be responding you there. So see you in the next one. Bye bye.